the development cycle for these new technologies is long. And because it's long, it's a historically underfunded competency in the United States. We do not like to invest in things that have a 10-year horizon, that are high risk, and that may be supplanted by some other technology developed elsewhere in the world. So it's not been going on here until recently. There's been a lot of money poured into this, and now there's a lot of good intention, though the folks who are well-intentioned, though, don't appreciate necessarily all the issues, in my mind, of what this means, what we actually have to do. And so it's going to be a while before researchers in the United States as a whole catch up with themselves. And one of the key aspects here, there's no Moore's law for battery. We're not going to double the capacity or the energy density or specific energy of a battery pack in any sort of routine amount of time. We are limited by the second law of thermodynamics, which is in turn limited by the quantum mechanical functionality of the electron orbitals that define the materials that we need to use. This is all, it really goes down to some very fundamental things. But anyway, just a quick segue now. In fact, I'm going to skip this in the sake of time. So ask me later. If you want to know more about how I test batteries and what we got going on, I got some really interesting results. We're going to forget about it, though. We also talked a bit about emissions this morning. And I'll briefly, this is a study that also came out of Carnegie Mellon, Costa Samaras, Steve colleague. And one of the points that we talk about is, and different folks have said, well, emissions are, and this is a really interesting finding in my mind, that if you use the current US mix of electricity supply and you compare the life cycle emissions between a conventional vehicle, a hybrid, a PHEV 30 and PHEV 90, conventional vehicle gives out more, but the hybrid and the two PHEVs are basically dead on tied, right? And what's interesting here too, the black and white diagonal hash, that's the energy footprint or the CO2 footprint associated with producing the battery. So you actually pay a significant cost for this PHEV 90, which is a very large battery. You pay some significant price for that as far as CO2 emissions go, right? This is per kilometer traveled. If we have a low carbon electricity, we do better with the PHEV 90. Carbon intensive electricity, you see much worse. And if we go to cellulosic, it's interesting, the conventional vehicle beats out everything but the hybrid. So the hybrid really is the winner in my mind when we talk about CO2 emissions, unless you have very low carbon electricity, which we do not. So until that time, there is a sort of not a very strong environmental argument given the current mix of electrons that we have right now in this country. So fuel cells. What do I think of when I think of fuel cells? I like fuel cells. They're a great technology. I think they are, it's an interesting and elegant way to circumvent the Carnot limitation for creating power from what should be or ought to be a combustion reaction. However, when people say hydrogen economy, in my mind, I think it's a platinum economy. That's because right now, there's only one known catalyst material class that has a combination of necessary activity, that is power production per unit material, and durability, the hours we might hope that it would last. And these are the noble metals that have very high platinum content. We are now alloying platinum with things like cobalt and nickel and manganese, things like that, that diminish the amount of platinum needed, but it's still significant. And there are some very interesting non-platinum catalysts on the horizon, but that's where they are. And it's not clear how soon we can use those. It might be decades, right? If we're lucky, and maybe not. I believe it's going to happen, but it's not something that is nearly as near term as other aspects of the fuel cell piece. And the corollary is that most of a fuel cell is platinum. Here's the cost per kilowatt for an 80 kilowatt fuel cell, and most of it is stack. If you look at the blue, that's the price per kilowatt total, and it's broken down. And most of this is actually just pure platinum. And so what does this mean? What's the long-term goal for platinum utilization in a typical size 80 kilowatt PEM fuel cell? This is an aggregated, some aggregate values from Directed Technologies and TX. These are DOE-sponsored studies. And it has come down dramatically if you want to believe. They basically, these folks aggregate recent results and try to interpret what they mean in the context of a mass-produced fuel cell stack or fuel cell system. And we're down under 50 grams per fuel cell. So I'll spot you 15 grams of platinum per fuel cell for an 80 kilowatt fuel cell. That's much lower than we can do right now. Let's assume it though. So how much platinum do we need then to displace a meaningful fraction of the existing US or indeed world driving fleet with PEM fuel cell cars, right? Some of you have probably seen this argument. We need a fair amount. right? The world platinum production is somewhere between 200 and 300 metric tons a year, and they are, they're more or less maxed out from what I can tell. And others might know more about the platinum market. It's sort of a convoluted market because there are only a handful of producers. South Africa, Russia, sort of dominate the platinum market. And so again, we place ourselves in some jeopardy in that regard. And if we want to have, if you look here, we need, if we converted relatively, maybe even 1 or 2% of our fleet per year to PEM fuel cells, we would drastically impact the amount of platinum needed, and we would almost certainly disrupt the platinum market. This is a problem for a number of reasons. And indeed, the platinum producers say, oh, sure, we can match that, but at what price? They're not saying that. And the other thing they're not saying is how it would bottom out other materials that are co-mined with platinum. Nickel and some other very common materials which have a particular price point would flood the market or be set aside by the platinum producers, and that, again, causes general materials instability. That's all I have. Indeed, one last thing. I encourage you to check out. This is another effort at Carnegie Mellon called the Charge Car, and this sort of falls under this larger group of people that we have going on, chargecar.org. And I hope it's linked eventually to the Toyota site. And what's great about this is that we already have a community of hundreds of drivers who are logging their daily urban and suburban commutes. And this website aggregates that and gives you a sense of what if you had a PHEV or an EV? What if you had different kinds of electric drivetrains? How much regen do you expect to gain depending on your altitude change? And it's really interesting. So I encourage you to go check that out as well. So that's it.